So Daniel and I are talking about crowding beyond excluded volume, a tale of two dimers, and I will talk about why it's important and the data. Daniel will then take over and talk about what the data mean. So now, why can't I change my slide? There we go. So why would we want to study this? For over 80 years, most of protein science has been done in buffer alone. That is, the solutes and co-solutes are less than 10 grams per liter. But cells are crowded. The concentration of protein in the bacterium E. coli is somewhere between 200 and 320 grams per liter. Now, mammalian cells it's less, but it's still high. For instance, if you ate an egg this morning, the concentration of protein in that egg was about 100 grams per liter. Oh, I see. I've got to change it with my mouse, not my keyboard. Here we have a simulation of what the inside of a bacterial cell might look like from Sugita and Feigen. You can find this on YouTube. You can see the proteins in there. You can see some small metabolites, and if you look closely, you can see some nucleic acids as well. So clearly the inside of a cell is not like a glass of water. So what I'll talk about is, one, that the classic model of macromolecular crowding is too simple. Then I'll talk about the systematic data we acquired to come up with a better idea. Then I'll do what you've all been waiting for, turn it over to Daniel. Okay, let's talk about protein folding, and let's talk about what crowding does. And we call this the elevator analogy. So globular proteins have only two thermodynamic states. This is why I've been studying them for many years, because it's a simple system. Proteins are either folded or unfolded, where the folded protein is compact and the unfolded protein is less compact, and they are in equilibrium with each other. If we consider this in just dilute solution, it's like being in an elevator by yourself. You can be compact, you can be less compact, all spread out like Joey is in this elevator. But then, if inside a cell, it's much more crowded, so that Joey can no longer be all spread out. He has to be compact. So what that means for protein stability is that crowding pushes the equilibrium towards the folded state. In other words, crowding should stabilize proteins. This is the classic explanation of what crowding should do. And you notice I didn't talk about any interactions between the molecules. They just can't interpenetrate each other, which means that classic theory predicts that this stability should occur entirely from the entropy. So now I want to talk about some observations that we've made over the years in cells. Graduate students in the audience should look away, because I'm going to summarize 6 PhD dissertations in one slide. If we look at protein stability inside living E. coli, we find that the proteins are actually a bit less stable than they are in buffer, not more stable, going against the classic observation. If we osmotically shock the cells, in other words, we suck some water out so they become even more crowded, the stability goes down even further. If we do the same thing in frog oocytes, of course, those are eukaryotes, so the concentration, so that these are less crowded than bacterial cells, we find the same destabilization that we see in bacterial cells. Turning to protein complex formation, in other words, the interaction between two proteins, we found that they become more stable in cells than in buffer under certain conditions. We also see that cells can actually change the reaction mechanism. For instance, in one of our studies, in dilute solution, two folded monomers go to form a dimer. But if you try to do that experiment in cells, the equilibrium becomes between two unfolded monomers and the dimer. And in every one of these studies, we always see an enthalpic effect, which is not predicted by simple theory. I want to talk now about some recent data that we have that is less complicated. Because let's face it, it's hard to do systematic experiments in cells. You can't just arbitrarily change the size or the concentration of things. But we can do some kind of experiments using a semi-reductionist approach. And that is by just increasing the protein concentration of one protein. And we did this with a model protein called GB1, and that's Jordan Markle next to the magnet who did all these experiments. So here's the protein we're looking at. It's a cute little globular protein called GB1. It's only 6.2 kilodaltons, has a PI of 4.6, and it's extremely well studied. Now, I have to talk a little bit about the thermodynamics of protein folding. So in the center of this slide, you see the native structure of GB1. Now, if you look at this equilibrium in the red box, this is the equilibrium of global unfolding. It's the two-state idea that I talked about before. This is the kind of stability one measures using differential scanning calorimetry, for instance. However, there's also breathing motions. In other words, besides the protein completely unfolding, it can breathe where only a certain part of the structure will be exposed. Now, we can detect that breathing using proton-deuterium exchange experiments. Let me talk about these. We have our nitrogen-15 enriched protein. And here is what's called its HSQC spectrum. On X, we have the proton chemical shift. On Y, we have the nitrogen chemical shift. These black dots, they are called cross peaks, and we get one from every amino acid residue except proline, because it doesn't have an amide proton. Now, this is actually a contour map, so that these cross peaks also have intensity, as I show in that inset. If we take our favorite protein and put it from H2O into D2O, then the protons of the really electronegative elements, like nitrogen, they will exchange in a base catalyzed reaction. So in other words, that proton will be ripped off by the OD minus, and it'll accept a deuterium from the D2O. Now, deuterium is not detected by proton NMR. So that means if we collect serial HSQC spectra, one after another, after we transfer into D2O, what we see is the volume of those cross peaks goes down. Now, we get this information for every cross peak in the spectrum so that we can plot the volume of the cross peak as a function of time for every residue we can observe. It's been known since the 1950s that you can consider this kind of reaction as I've written here. That is, we have an NH in a closed form, and it will open every now and again. And when it's in the open form, the H can exchange for a D, and then it can close again. If we assume that the protein is stable, we know it is for GB1. If we assume that the intrinsic rate constant, that is the rate constant for exchange from the open state, is rate determining, which we know from pH-dependent experiments, and if we know that this intrinsic rate is not changed by the presence of the Crowder, which we did many years ago, then we can take our K, then the K observed is equal to that opening rate constant over the closing rate constant times the intrinsic rate. We can get the intrinsic rate from tables. That is then, we can then get the equilibrium constant for opening, which in red we can convert to a free energy. So now that free energy of opening is the stability. For GB1, we know which residues only exchange their protons when the protein is fully exposed. Those are called global unfolding residues. This is worked out in the 1990s, and here we have a list of the residues that are only exposed when the protein completely unfolds. That means that the delta G we measure by this experiment is about the same as the delta G you'd measure by calorimetry. We've confirmed that. Then we have all these pink residues. They're locally unfolding residues, and that means that these are breathing motions. So in these, the opening free energy is less than the global unfolding free energy. We did this experiment. One of my graduate students, Ida Chu, did this experiment in polyethylene glycols, which are stabilizing, and she showed that actually what we do is we stabilize the entire protein. And we also found that what happens in polyethylene glycol crowders is that this turns the local unfolders into global unfolders. So the protein quits breathing and only has the choice to either unfold or not unfold. But now we decided to do the experiment in a semi-reductionist but biologically relevant way by just increasing the concentration of GB1. So we crowded GB1 with itself. We take N15 enriched GB1 at 3 grams per liter, very low concentration. And what we do is we then spike it with unenriched GB1 to these concentrations. Now you're wondering why they're not exact numbers. It's because we don't know what the concentration is till we finish the experiment. And these are all everything I'll show you today has been done in triplicate. That's why there are uncertainties. So to look at I should also say, many of you are thinking, hold on, Gary, if you increase the concentration of this protein, it's going to, they're all going to glom together and aggregate. We have shown using very sensitive techniques that there is no aggregation here. This protein remains a monomer. So on the x-axis, we have the residue number in GB1. And up above here, I've shown the secondary structure and the amino acid sequence. And the red letters are those residues that only expose themselves upon complete unfolding. And here we have the structure painted with the global unfolding residues. On the y-axis, we have delta delta G. That is how much the increase in concentration affects the free energy change. So it's the crowded condition minus the dilute condition. If the number is greater than 0, that means we're stabilizing the protein. If it's less than 0, it means we're destabilizing the protein. And here are the data, and the key thing to see here is that increasing the concentration stabilizes some parts of the protein and destabilizes others. This is absolutely against what theory says should happen. Theory says they should all be stabilizing. In fact, most of them are destabilized. And the ones that are destabilized are the local unfolders. The few that are stabilized, they are the ones that are only exposed upon complete unfolding. So this brings forth a quotation from the Bible, but I prefer quoting Billie Holiday, who said, "Them that has shall get, them that's not shall lose." In other words, there's a concentration dependence both ways. As you increase the concentration of GB1, those that are stabilized more, and those that are destabilized are also destabilized more. So the short explanation for this is that simple theory ignores chemistry. There are attractive interactions between proteins. They don't aggregate, but there are attractive interactions. Those attractive interactions will tend to unfold the protein. I mean, this is why urea destabilizes proteins, because it has an attractive interaction with the protein surface. The repulsive interactions occur because all these proteins have the same charge. So the idea of crowding is more complicated than simple theory would have us think about. The classic model is too simple. Enter my collaborator and friend, Daniel Harries. Here we are at our first meeting to get this collaboration together in Jerusalem a few years ago. We decided if we were going to solve this problem, we had to do something that is the death knell for most grant applications. We had to collect systematic data. And granting agencies don't like systematic data. They want you to cure cancer in one experiment. But we decided we needed to do this. We needed to choose several protein systems that would test different aspects of our ideas. One is protein stability, that is the difference between the folded and the unfolded state. We also wanted to look at the stability of protein complexes. We wanted to choose crowders where we could look at several different things. We wanted to look at several sizes. In other words, to come up with a model, we needed to look at the size effect of the crowding molecule. We needed some very special crowding molecules. We also needed to do this as a function of concentration. So the crowders we looked at had to be incredibly soluble, like 300 grams per liter soluble. And because we wanted to get at the enthalpy, we needed to look at several different temperatures. And we wanted very simple detection. So let me talk about each one of those. Protein systems. For stability, we chose this little protein domain called SH3. It's a rather small folded protein, and it has a beautiful equilibrium. Two states, folded and unfolded. Here we have a picture of the folded state. For the complex stability, we wanted to look at some variants of GB1. Now, I talked about GB1 in the self-crowding part just before, but many years ago, it was discovered that you can make a few amino acid substitutions in GB1 and turn it into a dimer. In fact, you can turn it into two different dimers. You could turn it into a very simple kissing sphere dimer, where this is the dissociation of the dimer between two folded proteins, and then we have two unfolded monomers. That's called a side-by-side dimer. We have a picture of it up here in red. Make several different amino acid substitutions, and you can make a domain swap dimer. I don't know if you can see my hands, but in other words, the side-by-side dimer is just some kissing spheres, where the domain swap dimer, they actually exchange secondary structure units, and you can see that here in this green structure. And I should also say that the domain swap dimer forms from partially folded monomers rather than fully folded monomers. Here's a cartoon of the side-by-side dimer. And then here's a cartoon of a reaction of the domain swap dimer, where we have both dimerization and folding going on. Now, those are the systems. What about the Crowders? Although they're not biologically relevant, polyethylene glycols, we reasoned, would allow us to test any model. That's because they come in many different sizes that have a very low polydispersity. We use 11 different sizes from 62 Daltons, which is ethylene glycol, up to 35 kilodaltons, and we don't go higher than that. And here's my former student, Claire, standing next to her collection of polyethylene glycols. They're very soluble. We can go from concentrations, everything we looked at is at least 5 concentrations up to 300 grams per liter, from 0 to 300 grams per liter. Temperatures, what I'll talk about today, 8 different temperatures from 283 Kelvin to 318 Kelvin. And like I've said before, all the data I'm going to show you has been triplicated. So, and the main point of me saying this is that even if Daniel and I are wrong, whatever theory is right is going to have to explain our data. Now, these are not physiologically relevant, but they're useful. And for you people out there that are interested in colloids, Daniel will talk about this, but the beautiful thing is because they're colloids, really gave us an independent test of our ideas. Now, the final thing was simple detection, because we're going to have to make thousands of measurements, and I want to have a system that is very easy to work with. And this is where fluorine-19 at NMR comes in. Fluorine-19 is 100% abundant. It's 83% as sensitive as a proton, and E. coli isn't very smart. If you feed E. coli 5-fluoroindole, which is cheap, it will turn it into 5-fluorotryptophan and put it into your favorite protein. So what you do is you add the indole at the same time you induce the synthesis, and bingo, your protein is labeled. Here I have the SH3, and I've circled its sole tryptophan. So therefore, we get one resonance for each state. We get a resonance for the folded state and a resonance for the unfolded state. And for you NMR jocks in the audience, they're in slow exchange on the chemical shift time scale, which means the integral is directly proportional to the concentration of the forms. Here is the spectrum of this protein. Now, its stability is about 0 kcals per mole, which means we can see both the folded and unfolded forms. We can integrate those resonances, divide the areas, bingo, we have the equilibrium constant, we can get the free energy. We do the temperature dependence, we can get the enthalpy. And here we have some spectra where we've changed the temperature, and you can see the population changes. Dimer, same thing. Here we have the spectrum of the side-by-side dimer. You can see the dimer peak on the left, the monomer peak on the right, at several different temperatures. We can, these are Van Hoff plots at the bottom, where we have reciprocal temperature versus the natural log of the equilibrium constant. And we see this in buffer and several, and in pegs at different concentrations. We also notice that they're not straight lines, which means there's a difference in heat capacity between the forms as well. The domain swap dimer, here we go. We see the same thing. We see 2 resonances. We can see them as a function of temperature. We can get the Van Hoff plots. Beautiful data. Here's what we get from the data. We get the equilibrium constant from integrating the resonances. We get the free energy from those. We get the delta H from Van Hoff analysis, and we also get the change in heat capacity. What I'll be talking about from now on isn't like delta G or delta H. It's the difference between the crowded and the dilute conditions. And I want to also say crowding does not affect the change in heat capacity. I'm not going to show you those data, but we can forget about that. We're just going to look at the changes in the free energy and the enthalpy. Here are the protein stability data, where we have polymer size on X and what crowding does on Y. And what we see is that as we increase the concentration of the polyethylene glycol, we see increased stability, but not in a way that is obviously predicted by simple theory. I should say here, the smooth curves are only to the aid the eye. Will fit. Daniel will show model fitting later. But now, turning to the enthalpy, we see that as we increase the concentration, we see an increase in delta delta H. And so the point here is that there's a size effect. It's steep and then shallow, saturates at high molecular weight. The stable, okay, maybe you missed this, but if you looked at the y-axis, the change in enthalpy was much greater than the change in free energy, which means that the increase in stability came from the enthalpy, not the entropy, as predicted by simple theory. And everything increases with peg concentrations. Small pegs are strange, and I'll talk about that. But the point here is this is inconsistent with simple theory, inconsistent with the elevator analogy. Now, turning to dimer stability, again, we have concentration on the x-axis. We're going to talk about the free energy on the y, and this is at just 298 K for the side-by-side dimer and for the domain swap dimer, and with all these different pegs. The first thing you notice, here's the side-by-side dimer data, is crowding isn't stabilizing, it's destabilizing. And for the domain swap dimer, it's almost the same thing, although with some of the larger pegs, we do see a very small stabilizing effect. I should say that that dashed line, the dashed horizontal line, that's the value in buffer. If we look at the enthalpy change of crowding, again, we say a bit of a stabilizing enthalpy change at low concentration, but then the enthalpy change becomes destabilizing. Same for the domain swap dimer. So the summary here, pegs are mostly destabilizing, and small pegs are the most destabilizing. There's always an enthalpic effect. Small pegs tend to be stabilizing, large pegs are destabilizing enthalpically. Again, inconsistent with simple theory. Now, these data are from the Pielak lab, and these are the people who collected it all. So let me just go through and thank them. So this is Jordan. I talked about her data with the self-crowding and the amide proton exchange. This is Thomas. Thomas did a lot of the heavy lifting on the PEG data. That's Owen. He also worked with Thomas. I should say Thomas and Owen are both undergraduates. This is Hania. She's taking over this project, another undergraduate. And as is Taryn. I'm going to turn this over in just a second to Daniel, but there's Daniel with his graduate student, Gil, who worked out the model for us. And I should have mentioned that beautiful machine in the center is my Moto Guzzi. Life is too short not to have an Italian motorcycle. Now, the people who made this, who have gone on to better things after this project, Claire is a postdoc at Stanford, Rinko's a graduate student at Yale, David is a program director at the National Science Foundation, Sophie is a graduate student in London, Francis just earned his MD, and Stu is our NMR facility coordinator. The NSF funded these data, funded this operation, even though it's systematic. And with that, I'm going to turn it over to Daniel, and there'll be time for questions at the very end. So I'm going to see if I can't get out of here and let Daniel take over. And to do that, what do I have to do? I have to stop sharing. I have stopped sharing.
Okay, so I hope you can see this. And thank you, Gary, for that introduction and cliffhanger. So how is it all working together? So in this part, I'll try to focus on the theory of the kind of data that Gary produced. He and the group were amazing at getting this huge amount of systematic data that includes our dream come true, the dissection into enthalpy and entropy in these systems that have really helped us to pinpoint, we think, what are the origins of the crowding effects in these systems. So in general, taking a step back and looking at the kinds of systems that we think we can approach with this strategy, we have the dimerization that Gary talked about, but we can also think about other cases where we see a compaction in a process. It can be colloids that form some kind of condensed phase. It can also be a protein folding or unfolding, as Gary showed. So in all these cases, we know already that temperature, pressure, and pH are going to shift these equilibria left and right. We are trying to think about what other chemical potentials can do to these equilibria. That is, when we add additional solutes, these can be salts, sugars, polymers, and various other organic molecules such as metabolites, osmolytes, and so on. So can we generalize and say something about these systems? So of course it's very hard to say something that is absolutely general, but let's focus on systems where the solutes are excluded from the large macromolecules or colloids, and this is what we would generally think of as crowding. That is, we have some limit on the available volume in the system, confinement, and so some image like Gary showed in the elevator, or maybe this one from a swimming pool with a lot of people in there. And you notice that they also have this soft interaction between them with this with these tubes that helps them float, but also adds to the interaction between different people in the swimming pool. So this analogy will become apparent when we discuss what we have to take into account when we think about models of crowding. As Minos mentioned already in the introduction, this is not something that is only relevant to biological or cellular environments where we know there is a high concentration of macromolecules. It's also relevant for colloidal systems. Specifically, I took a couple of almost random examples of the effect of crowders on colloidal assembly. This one is from the group of Shakin. You see these colloids in the absence of polymer and then in the presence of polyethylene glycol. And you see that apparently the addition of the polyethylene glycol promotes some kind of attractive interactions between the colloidal spheres, which is basically a depletion kind or crowding type of interaction. Here is another example from the group of Pine, whereby you can drive association between colloids of different shapes and sizes by adding, again, a polymer that crowds the solution and drives these kinds of associations. Here is another example from Ofer Manor at the Technion. So the idea here is that you can also drive an effective association between colloidal spheres, in this case polystyrene, that are crowded by nanoparticles, and that drives the large polystyrene beads to the interface, as you can see by this progression of increasingly larger concentrations of the nanoparticles, and you get stronger and stronger coverage by the polystyrene beads. So the relevance of crowding is quite wide, but we will focus mainly on these systems of proteins. But the origin of the models and theory for these originated with the colloidal community. And the traditional view of crowding can be traced back to the Asakura and Osawa model for depletion forces. And the idea is very simple, that it can be summarized basically by one slide. And the idea is that when you have co-solutes that are preferentially excluded from a colloid, a larger colloid here in yellow, you get this volume of exclusion, and this volume of exclusion can be minimized by bringing the two colloids together, so that the overall excluded volume is reduced in the process. This releases some of the excluded volume, which is now volume available to these co-solutes in solution. So basically there is a gain in this excluded volume, which then translates to an added entropy of the co-solutes. And so we can see from this basic model that stabilization scales with the concentration and size of the co-solute or of the crowder, because as you get more, gain more excluded volume from the dimerization or precipitation of the colloids, you get more free energy. And as the size increases, there is a larger delta V to gain from this process. And so this can also be translated to a picture whereby we think about the favorable free energy as being just the product of the osmotic pressure that pushes these two spheres towards each other and the exchange in excluded volume. And since the osmotic pressure in the Van 't Hoff limit is simply proportional to concentration, we find that stabilization should scale according to this model with osmotic pressure and excluded volume. Moreover, because there are only volume restrictions in this model, the effect is completely entropic. And so we should not expect any enthalpy to be part of this process of compaction. Then you might ask, okay, this is too simple. We have spheres. Maybe actually in the original formulation of Asakura and Osawa, these were just flat surfaces that were interacting. What if in the process there is also a change in the shape, volume and shape of the two interacting particles? For instance, like in this example, two spherical objects become ellipsoid. Well, in that case, an adaptation or some more intricate formulation in the form of scaled particle theory can give you the answer. Basically, instead of thinking about the osmotic pressure as pushing these two colloids towards each other, we can think about the work that is required to create voids or cavities inside solution, and we would compare then the work that is required to form these two spherical cavities with the work that is required to form this ellipsoidal one. And that was the basis of the crowding theory, as it was also formulated originally by Minton and then by many others. And the question is, does this hold? And if not, what is it that doesn't exactly fit the experiments? And I'm showing just an example of in this case, protein folding applied to this idea of Asakura and Osawa and the depletion force. So in this case, we're looking at this small mini protein folding and unfolding from a beta hairpin. And this is done in the presence of many, many solutes going from small, in this case, glycerol, to large, in this case, dextran 40K. And we see that as the Asakura and Osawa theory would predict, the slope of this change in free energy with co-solute or Crowder concentration, the slope becomes more steep the larger the Crowder. And here we see it just in terms of the slope itself, which is related to this change in excluded volume. Indeed, it fits what we would expect. Also, the concentration dependence fits this linear dependence of osmotic pressure times change in excluded volume. The problem starts sometimes, not always, when we think about whether or when we try to test the idea that this effect should be entropic. And for that, I'm using now the example that Gary showed for the SH3 domain in the presence of these different polyethylene glycols, and the folding and unfolding of this protein shows different kinds of dependence with temperature for conditions that include different amounts of the polyethylene glycol. This translates into these maps of free energy, enthalpy, and entropy that show that the effect is predominantly enthalpic, and entropy, in fact, goes the wrong way. So it is not helping the stabilization, but works against the stabilization. This then poses a challenge to the models, to the current models, and we would like to then formulate a model that will be able to augment or add to what we know about depletion forces, taking into account this additional interaction that the Crowders can have with the proteins that goes beyond the hardcore interactions. So the first thing that we can do is look at the different examples that are available in the literature and see when it is that enthalpy is predominant and when entropy is dominating. And what we found is that often, not always, but quite often, small solutes tend to show this enthalpic effect, while larger solutes tend to have entropic stabilization. And so this is one thing that tells us that probably in many cases, the limit of the larger solutes does often fit better to the original picture of Asakura and Osawa. While smaller solutes tend to have this added enthalpic effect, which often goes opposite of what one would expect from the Asakura and Osawa model. We can also use these enthalpy versus entropy types of plots that allow us to make the very fast distinction between these two cases where enthalpy is driving the stabilization and when entropy is doing it. As Gary mentioned, these kinds of trends are also seen in cells, either mammalian or bacterial. So now we have many open questions. This is basically the state of affairs once you realize that there are all these enthalpic contributions. And we would like to devise this model so that it is able to answer at least some of these questions. And there are probably many questions. Here are some. What determines the effect for different Crowders? When will it be enthalpic? When will it be entropic? And why? What is the underlying molecular mechanism that forms this distinction? Can Crowders be specific? So if there is an added interaction between the Crowder and the colloid or protein, can they have different effects on different proteins or colloids? So can we use this as a smarter tool than just through excluded volume interactions and drive specific interactions while leave others unaffected? And finally, in this short list that I came up with is the question about temperature dependence. So will heating help crowding stabilization or will it interfere? And again, this will be directly related to whether the effect is enthalpic or entropic. So I'd like to tell you a little bit about the model that we're proposing to think about these crowding effects. And from this idea of osmotic pressure acting between particles, this beautiful Asakura and Osawa idea, we will shift our perspective to solution theory. So we're now thinking about a solution that explicitly has a solvent and solute. And we're thinking about two regions where the solution behaves quite differently. One is the bulk domain, that is far away from the macromolecule or the colloid. And in the bulk domain, we basically just have solvent and solute, so solvent and Crowder. Then, close to our protein or colloid, we have a region where the Crowder can interact directly with the protein. And this can be through excluded volume interactions. It can be through other types of interactions. And this affected area we call the protein domain, and it is, and we have this parameter, this typical length scale across which the Crowder can interact with the protein. We call it A. And then we consider interactions in both the bulk domain and in the protein domain that have to do with interactions between the different components in solution. First, we have the excluded volume interaction. This is basically taking over this idea of excluded volume interactions from the Asakura and Osawa and implementing it in a solution theory kind of a perspective. And this is this excluded volume parameter. We can get information about this excluded volume, for instance, through densitometry, looking at the partial molar volume of a solute in the cases that it is small. When it is larger, for instance, a polymer, we can think about the radius of gyration, for example, as the typical length scale for that solute or Crowder. Then we have the non-ideal mixing parameter, chi, and that can be evaluated. It's a phenomenological parameter that we can get from, for example, osmometry. We are by now routinely performing vapor pressure osmometry that is also temperature dependent, so we know the enthalpic and entropic component of this chi. And by fits to this osmotic pressure, we can get this chi and also its entropic and enthalpic components. Finally, we have this parameter epsilon that represents the soft interactions between the Crowder and the protein. And this is something that we get from fits to the data. And I'll show you how we do that. And by this method, we can dissect all these different interactions because each one is derived by an independent methodology, the excluded volume, the non-ideal mixing, and this epsilon parameter. And through that, we get information that was lacking before, because we know now what is the interaction between Crowder and protein. Okay, so as a theorist, I'm allowed one slide with long equations. This is mine. What we use for the solution is a Flory-Huggins type of free energy that includes an ideal mixing and a non-ideal free energy that is related to interactions between the Crowder and the solvent. In addition, we have this epsilon parameter that is relevant for the interaction of the Crowder with the colloid or the protein. So with these parameters, we now solve the free energy of the system, taking into account the necessary condition for equality of chemical potentials in the protein and in the bulk phases. And after we perform this step of minimization, we can perform fits to the data. And I'd like to show you some examples of how we do that. So here is an example of two mini proteins, one that folds into a beta hairpin, one that forms this alpha helical structure. And in this case, we're looking at these proteins in the presence of a variety of polyols and sugars. And these lines through the data are model fits. And the only fit parameter is the epsilon, the interaction of each one of these solutes with the protein. And you see that the lines fit quite nicely in both cases. And the question is, how is this epsilon different? So already just looking at the data, we can see that the effect of the same solutes on the folding of this beta hairpin is larger by about twofold. And this is, even if you look at the per amino acid level or the size or the exposed area of these proteins. So that is already a clue that tells us that the epsilon has to be different, this interaction between the solute and the protein is different for the two proteins. And specifically, from this beta hairpin folder, there is an added repulsion that is not derived from the steric interactions. So there is an added repulsion to that of the size of the solute. On the other hand, for this alpha helical protein, the interaction is favorable, it's sticky. So basically the solutes of this type, sugars and polyols, stick to the unfolded state of this alpha helical former. So we see an opposite effect of the same solute on these different proteins, which signifies a specificity in the action of these solutes, something that goes beyond their excluded volume, which is the same or very similar for the two cases. Another thing we can do is think about how important are these interactions. So give some quantification to the effect. And what we find is that while the excluded volume interactions drive a very similar change in free energy, the contribution of the soft interaction is opposite and is of the same order of magnitude in this case as that of the excluded volume. So for these smaller solutes, the origin of this added interaction, these soft interactions drive stronger or weaker depletion effects or crowding effects, depending on the type of interactions these solutes have with the interfaces of these proteins. So now, after showing you this example of folding, we can move on to the dimerization data that Gary showed. And indeed, the GB1 protein can, the two variants can either show a side-by-side type of dimerization or this more complex folding plus dimerization type of interaction. And we would like to now apply the model to these systems, where the added complication, at least in the case of the domain swap dimer, is that we have two processes acting in tandem. We have folding and dimerizing, one together with the other. So what we see here is that, that we can take that free energy data, and again, these lines are fits to the data where what we leave as the fit parameter is the interaction between the Crowder or solute with the protein surface. And we see that the lines fit quite nicely, using this time interactions of these many different polyethylene glycols with the protein, either with the unfolded state driving or impeding folding, and with the fully folded monomer going to the dimer state. And what we see is that we can fit these data. We can also get the entropy and enthalpic components of this interaction. And then the question is, what do we learn from this? So first of all, you see that the fits go through the data, even though some of the data is very non-monotonic. There is this shift between two types of behaviors, and this can be explained by the model. So first of all, we find that soft interactions are significant, especially for the smaller Crowders. And as Gary mentioned, the smaller pegs are strange. Their strangeness comes from these soft interactions. And then the non-monotonic behavior is a result of the opposing effects of Crowder's unfolding and dimerization. So while the interactions aid the folding, the interaction between Crowder and unfolded state drive folding, they prevent dimerization or impede dimerization because of the interaction between the Crowder and the monomer and the dimer, the fully folded ones. So this is something that helps us dissect the interactions between the Crowders and the molecules that we're interested in. Is there anything else that can be learned from applying our model to this system? So one thing that we were very happy to see as an emergent property of the model is that it is able to predict the scaling of the domain size, this A, this length scale of interaction between the Crowder and the protein. So if we look at the change of this length scale with the Crowder concentration, we find that for large enough polymers, there is a dependence, and this has a limiting behavior, a limiting slope that is related to a scaling, a well-known scaling that is known as the de Gennes scaling for polymers in the semi-dilute regime. And so what we are able to see as an emergent property of the model is that while small Crowders, for small Crowders, we see that this region that is affected close to the protein is just related to the size of the solute with no concentration dependence. For large Crowders, and specifically for polymers, there is a concentration dependence that is just the scaling law that we know from de Gennes. If you like it in a cartoon, for small Crowders, just the size of the Crowder determines the size of the protein domain, while for these polymer spaghettis in the dilute region, all we have is the affected area is just related to the radius of gyration, while for the semi-dilute region, we have this mesh size that comes in, and it now scales as this de Gennes scaling, and basically acts to reduce this size of the affected region. And this is interesting, first of all, because it's an emergent property of the model, but also because it suggests that for high enough concentrations of polymer, we should see some kind of weaker or more shielded effect of crowding that we would not see in the dilute region. So now, just as the last final few slides, I'd like to complement this idea of the model, of the mean field model, with information we have from simulations to try and pinpoint where, at least in some cases, this added chemical or soft interaction is coming from. So we know that there is something beyond excluded volume, but what is it? So early on, we thought that a natural suspect for this added interaction would be hydrogen bonding. And specifically in water solutions, we could see in simulations that there is a change in hydrogen bonding of water with water molecules and between water and solute upon solute addition. So compared to water, and here we see the probability of finding a specific hydrogen bond configuration, we see a higher probability of finding linear water hydrogen bonds, water-water hydrogen bonds in the presence of polyols and sugars, while the hydrogen bond that is formed with the polyols is weaker. If we look around a specific solute, in this case a polyol, we find that the water molecules prefer to form these more linear, stronger hydrogen bonds with each other, while deferring the hydrogen bonds between the polyol and water molecules to the formation of more lousy hydrogen bonds that are not fully compensating for that interaction. How is this extended now to solutions that also have a protein in them? So first of all, we see in simulations that the polyols are excluded from the region of the protein. So basically, there is the formation of this water layer, basically a monolayer, around the protein. Before there is also presence of the polyol, of the solute. So overall, think about something like this. This is a snapshot from the simulation. We have the protein and then the solute, but in between there is a monolayer of water. And in this monolayer, the hydrogen bonding between the water molecules is stronger than in pure water. While again, rather weak or weaker hydrogen bonds are formed between water and this next layer of solute. And so what we have close to the protein is a layer of water that is even more, if you like, hydrophilic than bulk water, because the hydrogen bonds are stronger and it is harder to compete with these rather strong hydrogen bonds. What that means for the protein is that it has to look for interactions elsewhere, and specifically the formation of internal bonds inside this protein or peptide. And so overall, the one source of soft interaction, you see that the solute is one monolayer away from the protein, but it is still interacting effectively with the protein through this monolayer of water that has more linear hydrogen bonding and is then driving the folding, the excess folding of this protein, even though it is not just the excluded volume of this solute that is acting on the protein. So overall, this added soft interaction or halo, like those people in the swimming pool, is often related to water structuring at the interface, although, of course, there could be other mechanisms in other cases. So I think I've said all I wanted to say about the modeling and theory. I would like to give special thanks to Gil and Liel, whose data I was showing here and fits to the data, and this wonderful collaboration with Gary, his students Claire and Thomas, and also to the funding agency, specifically the Binational Science Foundation, that allowed Gary and I to play around in this sandbox of crowding. Thank you, and I'll be happy to take questions.